Alright guys, welcome to the Chapter 6 review. We're just kind of reviewing the exam questions to kind of help you with your corrections later on. So, alright, so for number 1, so a lot of these are true-false questions. A lot of these are conceptual, but then there are some calculation ones. So the total area under a normal distribution is finite or equal to a number. So again, this is a concept of normal distributions, is that they're bell-shaped, they have a mean that is in the middle, and they have an area equal to 1. So if you notice that even though this thing goes forever on both sides, it still has a finite area. And the area of a normal distribution under the entire curve is equal to 1. So it is finite, so this is true. The z-value corresponding to a number above the mean is always positive. So is that true or false? Well, if you draw the bell curve, right, in the standard bell curve, the mean is 0 in the middle. And you have positive z's on the right side, and you have negative z's on the left side. Alright, so the z corresponding to a number above the mean, so in this case like 1, 2, 3, is always positive. So this is true. Any of these z-scores are above the mean, and they will be positive z-scores, z-values. If it was below the mean, then it would be negative z-values. Alright, so this is true. The normal distribution crosses the x-axis. That is incorrect. Again, according to this drawing here, and I'll draw it again, it never touches the x-axis. It tries to approach it, but it never actually crosses it. So that is false. The central limit theorem applies to means of samples selected from different populations. So again, the central limit theorem says that if you take, a population, right, and you take a population with a given average of mu, and you take a bunch of samples in that population, right? Let's say you took 3 samples, right? And you did the x bars for each of those samples. If you were to average those x bars, then you would get, if you were to average those x bars, then you would get the average to be mu, if you were to do all the possible averages. And then you would get a standard deviation that is equal to the standard deviation of the population divided by the square root of the sample size. So this is all taken within the same population. It's not taken from different populations. So this is actually false. Approximately what percentage of normally distributed data values will fall within 3 standard deviations? This should say above or below the mean. So this is actually the empirical rule. So if you give myself a little bit more room here. So this is actually the empirical rule. So the empirical rule is basically the 68%, 95%, 99.7% rule. And that states that if you were to go 1 or 2 standard deviations, or 1 standard deviation above or below the mean, then you would cover 68% of the curve. If you were to go, 2 above and below the mean, then you would cover 95%. And if you were to go 3 above and below, 3 standard deviations above or below, then you would cover 99%. Alright, so in this case, 3 standard deviations would be 99.7%. The standard deviation of the standard normal distribution is, okay, so the standard normal distribution has a mean of 0, has a mean that is equal to 0, and a standard deviation of 1, because it goes by ones. So the standard deviation is 1. Alright, so that's it. It's just a conceptual question that you needed to know. Which is a property of the normal distribution? Select all that apply. So with a normal distribution, again, the mean is located in the middle. So in the middle you have the mean, you also have the mode, because the mode is where it's most popular, and it's most popular at the top here, and which is at that x value, and you have the median. All right, so all three measures of center are actually located in the middle. This is bell-shaped, so we can see that this is a bell shape, and its mean is located at the center. Uniform, it is not uniform. It is only, uniform is when you have a distribution with the same shape. So like if you have a distribution like this, see the shape is the values are the same everywhere. So this is like a constant kind of curve. So that's how a uniform distribution looks like, where it's all the same on value. All right, so the answers are A, C, and D. When the distribution is negatively skewed, the relationship of the mean, median, and mode from left to right will be what? Okay, so again, like we said earlier, if it's normal, then the mean and median and mode are located here. In that case, mean equals median equals mode. So that's if it's normal. If it's skewed right or positively skewed, then the curve will look like this, and which the right tail is longer. See, the positive tail is longer, that's why it's positively skewed, or skewed right, and the negative tail is shorter. So in this example, the mode is usually where the peak is. So this is where the mode is. The average is skewed right. That's why so the average is skewed in the positive direction because of the longer tail. So the average is, you know, around there. So we'll say that the mean, which is the average, is there, and the median is the middle number, so it's located in between those two. So you can see here that mode is less than median is less than mean. With negatively skewed, right, the negative tail is longer. And so again, like we said earlier, the median or the mode is located where the mountain is, or the peak. Since it's negatively skewed, the average is skewed left or negative, so the mean is there, and the median is the middle number. So for negatively skewed, we have mean is less than median is less than mode. And that is the answer to the question. The question is asking if it's negatively skewed, then the order is going to be mean, then median, then mode, from left to right. All right, what is the symbol for the mean of all possible means? So this is just a conceptual question. It's something that you either know or you don't. The symbol for the mean is mu, but the symbol for the mean of all possible means is mu x bar. And this is from the central limit theorem. So this is from the central limit theorem. According to the central limit theorem, what is the standard error equals what? So remember, the central limit theorem states that if you were to take, you know, if this is your distribution, right? Let's say that's your distribution of x values. If you were to take a whole bunch of samples from that population, then you'll get a distribution that looks like a bell curve, assuming you have enough samples, a sample size, but the mean is going to be given, all right, and then this is, the mean is mu here. Then the mean is going to be given by the same exact value for mu, because mu of the means is equal to mu. And the standard deviation is going to be given by the regular standard deviation divided by square root of n. So central limit theorem states that if you have a population with a mean of mu and a standard deviation of sigma, then if you were to do sigma x bar, which is the mean of the sample means, you would get sigma over square root of n. So this is what they're asking about. It's going to be equal to sigma over square root of n. The area to the right of the mean is indicated by, so this is multiple choice, but the choices aren't given here for these questions. So if you were to do a normal distribution, right, and you were to do the area to the right of the mean, so the mean is here, right? So if you were to do the area to the right, well, if we cut it in half, each of these should be worth 0.5. So the area to the right here is given by 0.5. And that's it. A standard normal distribution has which of the following properties? Alright, so the mean is equal to 0 and the variance is equal to 1. So like we said here, a standard bell curve starts out at 0 and it goes by 1s. So you have to know that the mean is 0 and the standard deviation is 1. And remember, the variance is basically, or the standard deviation is the square root of the variance. So like if the variance is 1, then the standard deviation is 1. So really, this is the same thing as standard deviation, if you think about it. The standard deviation is also equal to 1. The mean and the variance both equal 1. That's not true. The mean is equal to the variance. No, the mean is 0 and the standard deviation is 1. The mean is not equal to the standard deviation. So the answer is A. It's either you know it or you don't. One of those kind of questions. Let Z be a normal random variable. Determine the probability that Z is less than or equal to 1.4. Alright, so basically we have a bell curve with a mean of 0, standard deviation of 1, and our Z-score is 1.4, so around here. And we want the area to the left because the probability is basically the area. So we want the area to the left of that Z-score, since it says less than or equal to. So we looked this up on the probability chart. All right, so we're going to look this up on the Z chart, or the standard normal distribution table. We're going to look at 1.4. All right, so again, it says the table values represent area to the left of the Z-score. So that means that this is giving us the area to the left, which is exactly what we want. So therefore, whatever it gives us, this is going to be the answer. So we're looking for a Z-score of 1.4. So 1.40. So that would be 0.9192. So the probability that Z is less than or equal to 1.4 is what was that again? It was 9192. Alright, if it was asking for the area to the right, then we would have to do 1 minus that, because the area adds up to 1, and so to find the right side, we would do 1 minus. But here they're asking only for the left side. Alright, the area under the normal curve for P is Z equals 1.5 is 0, because you're only looking at the area under a single value. And that is simply true. So remember, we only have an area if we have an interval. So like if it was Z less than 1.5, then we would have an area to the left, right? And if we had Z greater than 1.5, then that would be an area to the right. But if we had Z equal to 1.5, well, there is no area. It's just a 1 value. So that means the area would be 0. So this is true. Let Z be a normal random variable with a mean of 50 and a standard deviation of 3. So the mean, oops, let me erase that. So the mean is 50, standard deviation is 3. The Z-score was determined to be negative 1.2. What is the value of X? So essentially, we're just plugging it into this formula right here. This is the formula for finding the X value given the Z. And this is actually in the formula sheet that was given in the exam. So that's the formula that you would use, which is 50 plus negative 1.2 times 3. And that's all you have to do. It's just a basic calculation. The formula was already given in the formula sheet. So 50 minus 1.2 times 3. So you have 46.4. All right, let x be a random variable with a mean of 35 and a standard deviation of 4. Determine the probability that x is between 30 and 37. So we have a mean of 35, standard deviation of 4. So essentially, you have 35 in the middle, and your standard deviation is 4, so you're going by 4 on each side. So this is right in the middle. And then you have 27 and 23. All right, so you're interested in 37 and 30. So you want the area in between those. All right, so what we're going to do is we're going to convert both of these into z-scores using the z-score formula. So we're going to convert this x1 into z1, and we're going to convert this x2 into z2. So the formula for z, again, we'll write it over here, is x minus mu over sigma. So we have z1 is x1, and x1 is 30. Mu is 35 divided by sigma. Here you get negative 1.25. Now we're going to calculate z2, so which is x2, which is 37 minus 35 over sigma, 2 over 4, so you get 0.50. So what we do is we look up both values in the table and we subtract both of those values, and that will give us in between those two values. So we look them up on the table. All right, so the way I write this is we want the probability that z is between negative 1.25 and 0.50. To find in between those, we subtract the value from the table for 0.50 and then minus the probability from the table for negative 1.25. So we look up both values on the table. All right. So we're going to look up 0.5. So for 0.50, it would be 0.6915. Then we want negative 1.25. So negative 1.2 and then 5. So that will be over here. So 0.1057, I'll round it. 0.1057. All right, and I will simply subtract those. And I will get 0.5858. 0.5858. And that is my probability that my x value is between 30 and 37 given those conditions. All right, number 17, what percentage of a normal distribution is found within a range of z-scores from negative 2 to 2? So again, this is the empirical rule. So it's just another question on the empirical rule, which is the 68, 95, 99.7% rule. So this is for one. So this is from negative 1 to 1. This is from negative 2 to 2 standard deviations, and this is from negative 3 to 3 standard deviations. So the answer is simply 95%. Suppose you're working with a data set that is normally distributed with a mean of 70 and a standard deviation of 10. Determine the value of x such that 65% of the values are greater than x. So we're trying to figure out we know that the mean is 70 and it's going by tens, right? So 80, 90, 100, 60, 50, and 40, and so on. So we know that the mean is 70, the sigma is 10, and we want to figure out the value of x so that 65% is greater. So we want 65% is to the right of x, right? So we know that the probability is so we know that the probability okay, so we'll just write it here. The probability is 0.6500. So that means it's probably, we can kind of guess where it is. I'll just guess that it's around here. We're just guessing where it is. We're going to figure out what the x value is, but this just for the purposes of illustration, I'm going to write it out here and draw it out. So let's say x is somewhere around here, and it's saying that the 65% is greater than x. So this area represents 0.65%. So if that area represents 65%, that means this area has to be 1 minus 65%. So 1 minus 0.6500 is 0.3500, and that's what this area represents. The reason I look up that area is because the table, the z-chart, only gives us that area. So we're going to look up 0.0350 on the table. So as you can see, we're going to look up the areas in the middle. So we got 0.3500 is probably it's close to this number so far. So yeah, this seems to be the closest value, 35197 versus 34827. So we will, so this is 197 off, and this is a little bit off. So you can choose whichever one, like they're kind of close to each other, so you can choose whichever one. I'll just choose the 35197, so that would be negative 0.38. Alright, so you could use negative 0.38 or negative 0.39. Either one is fine. So we'll say that the z-score is negative 0.38, approximately. Alright, so now we got our z, we can plug into this formula to get x. So we got 70 plus negative 0.38 times sigma of 10. So we have 70 minus 3.8, which is 66.2. So that means your score has to be 66.2 so that you can have, or the value has to be 66.2 so that the area to the right is 65%. All right, and I seem to have guessed pretty well. I put it right around 65, so this is actually pretty close to my estimate. All right. So let x be a random variable with a binomial variable with n equals 30, p equals 0.7. Use the normal distribution to approximate the binomial. Determine the probability of more than 16 but less than 25 successes. And they want you to use the correct representation. Okay, so this is a multiple choice question, but I eliminated the choices. So they want you to do a correct representation of the correction factor. So they want the correction factor for continuity. So they're asking essentially, if I were to use a normal distribution to approximate the binomial, how can I correct for continuity? So we know that they're asking for the probability that x is more than 16 but less than 25. So in order to correct for continuity, what we need to do, well, first off, let's go, I like to draw it out. So this is 16 and this is 25. So let's focus on the 16. We want to be greater than 16, right? So if we want to be greater than 16, let me just do the 16. So if we want greater than 16, then in order to ensure that we're strictly greater than 16, we're going to go a little bit to the right of 16 and then do the area to the right, all right? So that means that this is going to be 16.5. So far we have 16.5 for that correction factor. All right, now switch it to 25. Now we don't want it to be equal to 25, but we want it to be less than 25. So that means in order to ensure that I do not have 25, I'm going to go a little bit before it and then take the area to the left, all right? Shade to the left. So that means I'm going to go a little bit before it, so then I'm going to subtract 0.5 from it. So 24.5. All right, and that is my correction for continuity. All right, let x be a binomial variable. Using the normal distribution, what is the correct representation? Again, this is for the correction factor. All right. So we want the probability of at most 8 successes. So at most is less than or equal to 8. So we want to correct that. So we know that we want to be equal to 8. So I'm going to shade 8. And we want at most 8. So that means less than. So what I'm going to do is, to make sure that I include the 8, I'm going to go a little bit after it and then take the area to the left. And that'll ensure that I include 8. So that means that I'm going to add a little bit to 8, so I'm going to add 0.5 to 8. So then that would be 8.5. All right, and that's your answer. That's your correction factor. All right, 21. So let x be a binomial random variable with n equals 25 and p is 0.6. Use the normal distribution to approximate the binomial distribution. Determine the probability that more than 12 successes will occur. So we want the probability that x is greater than or equal to 12. Or more than, so greater than, sorry. So what we need to do is we need to test to see if NP is greater than 5 and NQ is greater than or equal to 5. This will ensure that we can use the normal distribution to approximate this. So we have 25 times 0.6 and 25 times 0.6 is 15, so 15 is greater than or equal to 5, that checks out. And then to find Q, you just, so Q is found by doing 1 minus P. So 1 minus 0.6, which is 0.4. So we have 0.4. All right, and this will give us 10. And 10 is greater than or equal to 5. So this checks out. So that means we can continue. So the next step is to calculate your mu and your standard deviation. So the mu we calculated over here, and that was 15. All right, so sigma, NP, we calculated that, that's 15, Q is 0.4. So about 2.45. All right, so we got the mu and the sigma. Now what we need to do is use the correction factor. So we're going to correct this. So again, we have 12. We want it to be equal to 12. We want it, or not equal to 12. So I'm just going to circle it but not fill it in. We want greater than 12, so we want over here. So to ensure that I do not have 12, I'm going to go a little bit after it and then shade everything to the right of that. So that means I'm going to add 0.5 to 12 and I get 12.5. So my correction is x is greater than 12.5. Why do I need this? Well, I need this because I need to calculate the z-score now. So I need to calculate the z-score, which is x minus mu over sigma. So my x is now going to be 12.5. My mean is 15. My standard deviation is 2.45. So I'm going to calculate my z now. negative 1.02. Alright, so that means remember, we want x is greater than 12.5, so basically we want the probability that z is greater than that. Okay, so if we were to draw this out, right, the mean is 15. It's going by about 2.5, approximately, so I'm just going to round it. And we want to be greater than 12.5. So 12.5 is, around here, and we want it to be greater than. Okay, so since we want greater than, what we're going to do is we're going to find the area from the z-chart. So from the z-table, the table will give us the area to the left. So to get the area to the right, we do 1 minus the table value. Okay, to get this guy, because we want the purple, all right? So we're going to do 1 minus the table value, and the table value gives us the left side, so less than. So I'm going to do 1 minus whatever that table value is from the z-chart. Negative 1.0, negative 1.02. So that's over here. So 0.1539. All right, so the 0.1539 represents the table value. So I'm going to do that in red so that you guys can see what that corresponds to. 1539. So that corresponds to the red, but we want the purple, so we got to do 1 minus that, which is 0.8461. And that's our final answer. Alright, so 22. Extreme values are not likely to occur in a normal distribution. Was that true or false? Well, again, like we said, if you were to draw out the bell curve, there's a very small chance that you're going to have an extreme value, which is why this curve is so tiny at the left and the right side, right? There's a high chance for you to have a medium-sized value, right? This is a high probability, so this is a big area. Whereas these are very tiny areas, right? So it's a very small chance that you're going to have an extreme value. So they're not likely to occur in a normal distribution. This is true. The measures of central tendency for a normal distribution are identical. So this is one of the properties, is that for a bell curve, the mean is located in the middle, and so is the median, and so is the mode. So they're all located in the middle, and they're all identical. So that's true. A normal probability plot is used to assess whether or not the sample data is normally distributed by determining if the points fall along a line. Again, this is a conceptual problem. So when you do the normal probability plot, if you get points that follow a line, then you can say that it's approximately normal. If you get points that are far off and have no definite pattern, then we would say it's not normal. Okay, so that's using the normal probability plot. So that would be true. The central limit theorem states that if n is large enough, the distribution of sample means follows which distribution? So if the n is large, so the n increases, then the distribution approaches the distribution of sample means becomes a normal distribution. And that's part of the central limit theorem. And the mean of that sampling distribution is going to be given by mu, and the standard deviation of that sampling distribution is given by sigma over square root of n. Alright, so the answer to the question is it's going to follow the normal distribution. The standard deviation of the sampling distribution is called what? So they're saying that, what is this guy called? That guy. So that guy is called the standard error. So that's a vocab question. So that guy is called the standard error. All right, increasing the sample size causes the standard deviation of sample means to do what? So again, the standard deviation of the sample means, or the standard error, is given by sigma over square root of n. So as we increase the sample size, as we increase n, what happens to this? Well, as we increase n, denominator gets bigger. If denominator gets bigger, then this gets smaller. So as we increase n, this guy gets smaller. So it's going to decrease. If a population has a mean of 350 and a standard deviation of 25, find the probability that a random sample of 40 will have a mean between 335 and 375. So they're asking for it to have the probability that it'll have a mean. So really, what they're asking for is they're saying find the probability that there's a mean between those two numbers. So this is a central limit theorem problem. All right, and the mean is 350 of the population, and the standard deviation is 25 for the population. And we have a sample size of 40. All right, so really what they're looking for, so we have a bell curve. In the middle, you're going to have 350, but the spread is going to be different. The spread is not going to be 25, so the mu x bar is equal to mu, which is 350, which is why we label 350 in the middle here. But the spread is going to be different. The spread is going to be given by sigma over square root of n. And sigma is 25, square root of 40. So the spread is going to be given by that number. So we'll round, so this is 3.95. Yeah, so this is about 3.95. Okay, so I'm going to round it to 4 when I add it. So this will be 350. I'm going to round it to about 4. So this will be spread out by about 4. So 354, 358, 362, 346, 342, and 338. All right. So now we know what the spread is, about 4, and we want it between 335 and 375. So 335 is, around here. It's below 338, and 375 is pretty high, actually. So 375 is all the way over here. So it looks like we have a large portion of the curve. So since we have a large portion of the curve, this is probably going to be very close to 1. So it'll be 0.999 something. So let's go ahead and calculate it. So we need to convert these to z's. So that we're going to convert that to z1, we're going to convert that to z2. So z1, remember the formula for z. Formula for z is x bar minus mu over sigma divided by square root of n. So that's from the formula sheet. So we have x bar 1, which is 335, minus the mu is 350, and we already calculated sigma over square root of n, that's 3.95, and then we'll get what that number is. Z2 is going to be x bar 2, which is 375, minus 350 over the sigma over square root of n, 3.95. So we'll calculate those values. Negative 3.80. And this will be 6.33. So these are pretty large values. So we want the area between those guys, right? So we want the probability that z is between those. So we want to subtract the area for 6.33 and minus the area for 3.80, negative 3.80. So we want to subtract those. So we're going to look them up on the table. So 6.33. Notice that the table doesn't actually give you 6.33. The highest is 3.9. And so we're going to end up rounding our number to 2.9999. So we'll say it's about 0.9999. And then for negative 3.80, again, we have negative 3.80, which is 0.00007. So we'll just round it to 0.0001. So this is 0.9998. So which is basically most of the curve. And that's your answer. And this makes sense from the graph. Suppose that 65% of all college students have an iPod. What is the probability that a sample of 50 will indicate that more than 30 students own an iPod? All right, so more than 30 students own an iPod. So if you notice that so either the students own an iPod or they do not own an iPod. So this is a binomial distribution. All right, so they either own an iPod or they don't. So binomial means two. There's two choices here. So we have the probability of success is 65%. The probability of failure is, means that they don't own an iPod, is 1 minus 65%, which is 35% or 0.35. They tell us the sample size is 50, and we want the probability that X is greater than 30, that there's more than 30 students. So we're going to use the normal approximation to this. So we're going to first test to see if this is greater than or equal to 5. If this is greater than or equal to 5, then we can use the normal approximation. So we have 0.65, oops, n is 30, so 30 times 0.65 which is 19.5, so that checks out. 30 times 0.35 which is 10.5, and that checks out as well. So we can use the normal distribution to approximate this. So therefore, we're going to go ahead and continue. So in order to do that, we need to calculate the mean and the standard deviation. The mean we already calculated, that's 19.5. All right, and then we need to do the square root. So let me rewrite this. So the standard deviation is the square root of NPQ. NP is 19.5, Q is 0.35. So we can get what that number is. .61. All right, so we got those two. Now the next thing we want to do is we want to use the correction factor for this guy. Okay, so if we were to do a number line, we have 30. We are not going to include 30, but we are going to do greater than 30. So in order to make sure that we do not have 30, we're going to go a little bit to the right of it and then shade to the right. All right. So that means that we're going to add a little bit to 30, so 30.5. So we're going to add 0.5 to it. So that means the correction factor is P is X is greater than 30.5. So now if we were to do the curve, right, we want to do 30.5, and we want everything to the right of it, okay, since we want greater than. So we're going to convert that to a z, so we're going to calculate the z. Z is x minus mu over sigma. So x here is 30.5 minus mu over sigma. So here I get a z-score of 4.21. So we want the probability that z is greater than 4.21. Remember, the table is going to give you the area to the left. This is going to be the table. But we want the area to the right, so we got to do 1 minus the table value to get the area to the right. So we got to do 1 minus the probability that z is less than. Alright, so look that up on the table. But if you look in the table, the highest is 3.9, so we're just going to use 0.99999, okay, as our value. So 0.9999, which is, you know, very small, 0.0001. All right, so a very small chance. All right, the average GMAT scores for the top 30 ranked graduate schools of business are listed below. Calculate the Pearson coefficient of skewness to determine the shape of the distribution. So, in order to do this, we need to use the Pearson coefficient of skewness formula, right? So the formula for PC, or Pearson coefficient of skewness, is 3 times x bar minus median divided by the sample standard deviation. All right, so we can find the x bar and the s from a calculator. So if you were to do this on a calculator, there's a function that you can use on the calculator to find these two. So I'm going to find those on the calculator. Again, if you wanted to do it on the TI, the TI 30X, what you need to do is you need to use the data key. You need to use the data key, and you need to so you need to use the data key, enter your data in there, and then you want to use stat var, you know, to find it. So there's keys on the calculator that you can use for that. But we're just going to calculate it. All right, so I went ahead and put it on the calculator, and I calculated the mean and the standard deviation, and those are the numbers that I got. Okay. So then what you want to do now is you want to find the median. So the median we're going to find, you know, the old way, you know, the old style. So we're going to sort this from smallest to largest. Okay. So I'm going to quickly sort this from smallest to largest, and then I'll pause it and show you guys. All right, so I went ahead and put them in order from smallest to largest, and this is what I got. So now once you sort them from smallest to largest, you want to figure out what the middle is. So you're going to start crossing out. So 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So that's our median right there. So our median or middle number is 688. All right, so then we're going to go ahead and plug these numbers in. So 3 times 678.13 minus 688 over 26.78. So I get about negative 1.11. So about negative 1.1. All right, so the way you know what the skewness is, if the PC is 0, it's exactly normal. If the PC is greater than 1, or greater than or equal to 1, approximately 1 or greater than, then it's significantly positively skewed. And if the PC is less than or equal to negative 1, it's significantly negatively skewed. So in this case, it is skewed to the left or negatively skewed significantly. All right. 31. The average repair cost of a microwave oven is $55 with a standard deviation of $8. The costs are normally distributed. If 12 ovens are repaired, find the probability that the mean of the repair bills will be greater than $60. All right, so the average repair is 55 with a standard deviation of 8. So n is equal to 12, so 12 ovens are repaired. Find the probability that the mean of the repair bills is greater than 60. So the probability that the mean is greater than 60. So this is a central limit theorem problem. So we want to figure out what we know that the mean of the sample means is 55, which is the mu. But the mean of the standard deviation of the sample means, or the standard error, is sigma over square root of n. So we got to calculate that. So that's 8 over square root of 12. So I get about 2.31 for the standard deviation. All right, so that's our standard. Now we're going to basically, I'm just going to draw it out so that we know what we're dealing with. So the mean is 55, and we're going about 2.3. So 57.3, 59.6, 61.9. So 2.3. So 52.7-ish. 50.4, and so on. So we want greater than 60, so 60 is around here. We want greater than. All right, so we're going to convert this to a z-score. So we got to convert that to a z. Right now that's an x bar. So we need to use the z-score formula, which is that. So x bar is 60, mu is 55, sigma is 8, and n is 12. So we already calculated this. That was this guy. All right, so I'm just going to replace that with 2.31. All right, so we can figure out what that is. So you get a z-score of about 2.16. All right, so that means that we want the probability that z is greater than 2.16. So remember, that means that we want the area, the table is going to give us the area to the left. So this is what the table is going to give us, but we want the area to the right. So to find the area to the right, we do 1 minus the table value. So 1 minus the probability that z is less than 2.16. All right, so let's look up the value. 2.16. 0, 1, 2, 3, 4, 5, 6. So this is 2.16, 0.9846. All right, so 1 minus 0.9846, so 0.0154. All right, and that's your answer for number 31. And we're down to the last one, so 32. The membership in an elite organization requires a test score in the upper 30% range. If the mean is 115 and the standard deviation is 12, find the lowest acceptable score that would enable a candidate to apply for membership. Assume the variable is normally distributed, round to the nearest whole. All right, so essentially we have, we know that the mean is 115, standard deviation is 12. So we know the middle is 115, and we know that we're going by 12s. Uh, 103 minus 12, so it should be 91. and then the 12, that's 79, and so on. All right, 1, 2, 3, there you go. All right, so now we want the lowest acceptable score that would in the upper 30%. So upper 30%. So probably means if it's upper 30%, you know, it may be, you know, around here. I'm just going to guesstimate. We got to figure out what that x is. That x is so that the upper part of the curve is 30% or 0.300. Okay, so that has to be 30%, which means that we need the table value on the left side. Okay, so to find the table value, we got to do 1 minus, right? So 1 minus 0.300 is 0.7000. So we got to look that up on the table, and that'll give us the z-score. Right, so let's look that up on the table. So we need 0.700 for the area. Okay, this is 002. Let me calculate that real quick. .69. All right, so I'm just gonna, you know, we have two choices, either one of these, right? So you pick one. This one's a little bit closer, so I'm gonna choose that one. But it doesn't really make that much of a difference because this will be 0.52 and this will be 0.53. So we're gonna use 0.52 because that seems to be the closest, but you can choose either one. So we get z is about 0.52. So z is approximately 0.52. So now we can use the x formula. Remember the x formula here, we used that earlier in another problem. So we have mu is 115, the new z that we found, and then times 12. And we're going to round that to the nearest whole number. So I got 121.2, which I'm going to round to 121. All right, and that's it for the test. This is just a review of all the questions that was on there. A lot of different concepts here for Chapter 6. All right, see you guys later.